the next thing that we would like to discuss are multiple equation models. On the whiteboard, we have been derived the seemingly unrated regression framework, abbreviated SUR, and this is what we would now like to implement also in MATLAB. So our task is use the exact returns of the first 25 stocks of this survivor stock matrix and implement a multiple equation model using time series regressions. Test whether the intercepts of the 25 equations are jointly significant. This is what we would like to do. We have here also our notes just to remember. So we have multiple equations. We have our capital N is 25 because we have 25 equations for each single stock. In each equation, we use again the Farmer and French three-factor model as an example, which means we have a constant as first regressor. Then we have the excess market factor as second regressor in our regressor matrix X. The third regressor is the size factor. And the fourth regressor is the value factor. So each regression equation, obviously, for each asset has the same risk factor matrix. And our U in the end of the right-hand side of the equation here denotes our residuals. It's the residual term, which is again assumed to be distributed with zero mean and standard deviation that is depending on the equation. For the first one here, it's sigma 1 square. For the second, it's sigma 2 square. And for the last is sigma 25 square. So we assume a constant variance for each residual, for each equation. So our hypothesis looks like this. Our null hypothesis is because we're interested in. The question is, can the Farmer and French three-factor model can it price these 25 stocks of our data set correctly? If it can, well, then obviously the intercept terms would be jointly zero, because if the Farmer and French effective three-factor model can explain the return evolutions of our stocks completely, obviously then these guys here would be zero. That's what our first hypothesis or our null hypothesis postulates. The alternative hypothesis, or the H1, is that at least one of these intercept terms is unequal to zero. Then we discussed the test statistic, how it looks like. It has this form. It looks quite fancy, right? And we then on the whiteboard, we basically then derived each single component that is an ingredient here in this formula. And on the whiteboard, there was a small typo. There was one inverse sign missing. So obviously here, this guy here, the term this xq transposed times what is here in parentheses times xq, this guy in parentheses is also inverted. So we have two inversions here. This on this formula here is the correct one that you might know. So how to implement this in MATLAB? So again, we have here our script, the place where we can write our MATLAB script. The task number 8 is then multiple equation models. Multiple equation models, and we have here the SUR model, a seemingly unrelated regression technique that we are interested in investigating. So first of all, let's define our exact return matrix. It's defined as Y1, if you remember correctly. So, and we want to have only the first 25 stocks from that matrix. So let's define this matrix as Y11 as a submatrix y11 is a submatrix of y1. So we want to have all time series observations. So we write double point, comma, and the columns 1 to 25, because there we have the corresponding stocks that we want to have in our subsample. So next, t is the length of y1, but actually we don't need to define this because it's already defined in the workspace, right? So n is now 25, n is the number of stocks in our sample. K, let's define the parameters for each equation. So we have 4 parameters in each equation, three beta exposures and 1 alpha, so it's four regressors, 4 parameters. So K is 4. Next, we want to define our regressor matrix X, and we have already done it earlier, but let's do it one more time. So it's once, in parentheses, capital T, 1. So we want to have a column vector, one column vector that has T ones. So it's a 497 by 1 vector. And we want to also to add our risk factor matrix, because we want to have these guys here, our 3 risk factors here, and here a vector of 1 that captures the intercept term in our regressor matrix. So then we want to create a huge vector, a column vector. Let's call it B hat. Here in B hat, we want to store each OLS regression equations parameter vector. So we have to do it in a for loop. So we want to equation by equation, we want to estimate the corresponding parameter vector. So what we'll get out of that of the first guy here is a 4 by 1 vector, right? Corresponding to alpha 1, beta 1, beta 2, and beta 3. Right? It's a 4 by 1 vector. And we want to stack each of these vectors here that we get from each single OLS regression into a huge vector. Because we have n equations, capital N equations, and 4 parameters to estimate. We have our overall vector here, this column vector, will have 25 by 4, which is 100. This will be 100 by 1 vector. Beta underscore hat will be 100 by 1 vector. So if I write now these parentheses here in MATLAB, it says that that's an open matrix. So it means, okay, I want to store here in something, and I do not want to define how big it becomes. So obviously there are always different ways how you can write the code and how you can construct the corresponding matrices here. But this is just one possibility, okay? We keep our options here open. So, but we know, okay, what comes in here, it should have, what comes out here, the beta underscore hat, in the end of the for loop, it should have something like 100 observations, and they should be in a row, in a column vector. It would be 100 by 1 vector. So next, what else do we need? So we need obviously a matrix where we store for each single equation the corresponding residual vector, which has also the dimension t by 1, because each single equation has the dimension t by 1. So we want to store all this in a matrix, so we need a matrix that gives us t time series observations and n columns, because we have n stocks. So for each column, in each column, we store the corresponding residual vector of each equation. So we want to have a zero matrix that has t rows and n columns. So next, we want to determine, so which is the guy in each equation here that we are interested in testing. So it's always the first parameter, the first out of 4. So now we have to determine this we have to indicate it in this R1 vector. So, and obviously it must be a 1 by 4 vector. So if you now copy this into our command window, And MATLAB spits us out what it is. So it's a 1/4 vector, and it indicates us where to find the corresponding parameter in each equation. So it's always the first one. So next we start our for loop here. We now regress equation by equation each single excess return vector on our risk factor matrix here that we here defined. So we start, I is going from 1 until capital N. Our popular formula for the OLS regression is X, our regressor matrix, transposed times itself inverted times itself transposed times capital Y11, and we start with all rows in the first column, and we know in the first column, in the rows we have the time series observations. So if I is 1, this will be here 1 in the first iteration, and it gives us the excess returns across time for the first stock. Okay, I is 2 in the next iteration when we end the for loop here. So it would give us then, this is the same obviously, so it would give us here then this goes to 2, and it just depicts from our Y11 sub matrix the second column, which are the excess returns of the second stock. So then now we have our estimated beta parameter for each respective equation. So now we want to have also the regression residuals. How are they defined? I call them now E underscore hat. What is it? Well, it's the excess returns from the corresponding stock I, right? Minus the regressor matrix times the estimated beta. Yeah, it's our well-known formula. Yeah. Then we say, okay, we grab this point estimator beta and stack it into our beta underscore hat matrix. So this is how you write it. So you write beta underscore hat. What should it be? So we put in what has been in it already before, and that's nothing obviously, but we have to write it anyways. And then this b, our estimated point estimator from here. Yeah. So this is nothing obviously because it was an empty matrix, and we stack under nothing or under what has been previous in it the new vector, which is a 4×1 vector. So this is empty, and now we stack into something that is empty, a 4×1 vector. So after the first iteration, this guy here will be 4×1. After the second iteration, this guy here is what has been 4×1. Yeah, it's now here. It's stored obviously, and we put in something that is 4×1 in under something that is 4×1. Which means this guy here is after the second iteration 8×1, and after the third iteration it becomes 12×1. Yeah, after the last iteration 21, when n is 21, this guy here has the dimension 100×1. It always stacks the vector of each iteration under the other one, and this is what we do by this comma. That's why we have here a comma. If you would here have a colon, we have here a colon. If we have a comma here, it would stack everything in a row vector. So we can, let's just check it, that you have seen it. So copy this into the workspace, here into the command window. And here it says matrix dimensions must agree. So what is wrong here? Let's see what is wrong here. X transposed X inverted So this must be obviously in this sign here. We have to take this to the power of -1. This guy is inverted, so now it should be correct. It can always happen that you miss something in the code, but then MATLAB will spit you out a error message. So now everything works out, obviously. So let's check out our beater underscore head. This is this guy here. Yeah. And let us just do it one more time. Now our beta head, it does not store everything how it should, right? So let's see where is our error here. So this is correct. This is correct as well. Okay, here we have to write double point. Yeah, in this for loop here, I is from 1 double point n. Okay, there was the error. So one more time, let's copy the code so far into the command window. And now you see, now it's correct. So now our beta underscore head vector, yeah, you see, now it has the correct dimension. It's 100 by 1 vector as we want to have it. So now, as I told you, if we write here a comma, it stacks everything into a row vector. Let's just do it for fun so that you see what's going on here. So you see now it stacks in after every single round. It takes the vector and stacks it basically as a 4 by 1 vector next to each other. So this has then the dimension 4 by 25, right? Yes. So that's basically how it looks like. But we, in our formula, so how the test statistic is constructed, so we need obviously this beta here is our beta underscore head, yeah, and it must have the dimension, yeah, 100 by 1, yeah, because this guy here is 100 by 1 vector in our test statistic. So let's make it correct. So write a comma here. So now we have stored our beta underscore head. This guy, yeah, that we need here for our test statistic. Next, we want to store, obviously, in order to construct this sigma head here, which is inverted here in this equation. In order to construct the sigma head, we need also the residuals for each equation. So we need the regression residuals for each single equation that we want to store here in this matrix that has zeros. So let's store it. So in each iteration, yeah, so in each iteration in each column I, what we want to have, we want to put in our E head, yeah, which is the corresponding, which gives us here the corresponding residual vector for each equation. Okay, so let's just run it one more time, including now all ingredients. And now we can check what is E, our matrix E. It should have now the dimension, obviously, T by 25, right? Here we find it. So obviously, it has 25 columns as we want to have and 497 time series observations. So that's also correct. That's great. So next step is we want to get this sigma matrix here. Yeah, we want to estimate the sigma matrix. So let's define it as sigma, and it has the dimension n by n. right? Because we have n equations. It's so a zero matrix n by n, yeah, and there we store in the corresponding sigmas for I is 1 until n. And you remember now, this is obviously something similar we have done for the omega matrix, right? But now it's slightly different. For j is 1 to n. So we have two for loops. So sigma ij, what should it be? Well, take the whole vector in the column I, transpose it, so that because this vector here obviously is a t by 1. This is a t by 1 vector. We have to transpose it as a 1 by t because we want to have in this matrix only numbers, right? Because on the main diagonal are the variances, yeah? On the main diagonal are the corresponding residual variances, yeah, on the main diagonal of this set. And above and below the main diagonal are the covariances between these residuals, yeah. So the element 1, 2 is the covariance between this guy and this guy. And the element 1, 3, in the first row, the third column, is the covariance between the residual of the first equation and the residual of the third equation, and so on. And we know already the covariance matrices have something in common. They are symmetric. So if you transpose them, you get the same thing again. So now we multiply it with E, and now we want to have the J, the column J, right? And we have to divide it by capital T. So this code tells you, okay, we have to go through our vectors here. So in case when I is equal to j, when that's the same, yeah, when that is the same, then we are on the main diagonal, obviously, yeah, and then it is just itself squared, yeah. When I is 1 and j is 2, yeah, when I is 1 and j is 2, it takes the residual from the first column, transposed it, and multiplies it with the residual vector from the second guy, from the second equation here, and it's divided by number of t. And what we get is the covariance between residual 1 and 2, and so on. And you can go through this code, so it does for all the other items as well. And what we get in the end is the covariance matrix of our residuals. Yeah, but obviously you see here in the formula it is inverted, yeah, but this is what we will talk about soon. So now we have constructed our sigma. Now we want to construct our R. So this guy here, right? And this guy here, we need for depicting from each equation the corresponding alpha parameter. Yeah. So and our R is defined as Kronecker product from what? Now we take the identity matrix, which has the dimension n because we have n equations, and R1 we have already defined earlier. How the Kronecker product works, we have derived in detail on the whiteboard. You should know that by now. So what we get out is here, it's a n by n times 4 matrix. So it's a 25 by 100 matrix, yeah? 25 by 100. And it must be like that because our beta is 100 by 1. So we have to multiply it with something that has 100 columns, right? So this guy here is R is 25 by 100, 25 by 100 times 100 by 1. So what comes out here is 25 by 1. Yeah? And this makes sense because we have 25 parameters to estimate, 25 alphas. Yeah? So that's how it is. So next, so let's say the formula, very simple, obviously. Yeah, we just need the Kronecker product. Yeah, we multiply the identity matrix with our predefined R1 vector here, which gives us again, which gives us which parameter in each equation is to be tested, and it's the alpha, it's the first one. So next we want to construct this block matrix, this guy here. Yeah, we have discussed in the lecture that our XQ here, that's a block matrix, yeah? And this has the dimension n times t by n times 4, because we have 4 parameters. So the dimension is then obviously we have 497 times these observations. This is t, and n is 25. So the dimension should be 497 times 25, and this is our row dimension times 25 by 4 times 100. So the dimension should be 12,425 by 100. That should be the dimension of our matrix, this guy here, this XQ. Let's define it as XX, yeah, and it's the Kronecker product from, again, our identity matrix of dimension n and our regressor matrix X. Because the regressor matrix is always the same, we can simply do this operation here. It's the same for all assets. Again, the dimension is obviously n times t by n times k. So let's do this. Let's copy this and see if everything is correct. So let's see our XX. What's the dimension? Here, yeah, it is exactly what we want to have. It has the dimension 12,425 by 100. And our R has the dimension, let's see, where do we find it? We have now so many. Yeah, it's 25 by 100, exactly how it should be. So everything seems to be correct. So next, so now we have this guy here. We have a sigma hat. We still need to invert it. We have this XQ. We have our R. We have our beta. We have to define a vector of zeros, yeah, because under the null hypothesis, all of these guys, these 25 guys, are 0. So this guy here should be a vector of zeros, right? Our R here in this equation, this guy, should be a vector of zeros, and it should be n by 1 vector, n by 1 vector of zeros, because we have n assets. So next, we want to take obviously here we have to take the inverse of our sigma. So let's define it as sigma 1, sigma underscore 1 should be our sigma matrix to the power of -1, which means take the inverse of sigma. So next, we define, now we have our inverse here. Now we define this inner expression here. The sigma hat inverted Kronecker product identity matrix of dimension t, which is here in the middle of the test statistic. So it's very simple. Let's call this guy Q and define Q. What should it be? Well, Kronecker product again times sigma, the inverse of sigma, which is sigma underscore 1. We have just defined it. And the identity matrix, now we have to take the dimension t. Close the parentheses and the next one as well. So that has now a huge dimension. So the dimension should be n times t by n times t. Because this guy here has the dimension n, and this guy here has the dimension t. So if you take the Kronecker product, what comes out is n by n times t by n times t. So we have 497 times these observations and n stocks. So the dimension is obviously 12,425 by 12,425. Now we have obviously all the ingredients that we need for our formula here, for our test statistic, yeah, which tests everything, which tests these guys here jointly. And again, why do we need it? Obviously, we need it because the alphas may be correlated. Yeah, there are a whole bunch of covariances that are here basically that are a part of this test statistic and which you find here. Yeah, so this guys here, we discussed it in detail on the whiteboard. Yeah, it gets us the corresponding covariances of these parameters that are to be estimated. This is always the case when you have a joint test of parameters. Yeah, there are always some covariances that we have to take into account when setting up the test statistic. So, and this is a walled test. Yeah, we also discussed in the lectures, you might remember, the so-called LM test, which is slightly different, but the outcome should be the same. So now we have to write this as a code, yeah, into MATLAB. So how do we do it? So let's call it lambda. What should it be? It should be R times beta underscore hat minus R transposed, right? Yes. Times R times this block matrix X Q transposed times this guy here in the middle that we have defined as Q times Q times X Q, this guy here. This should be transposed and now, sorry, this should be inverted. And now remember that on the whiteboard, yeah, we missed this. Yeah, so, but this is the correct thing. You should invert it times R transposed, right? Yeah. And now we have to invert this parenthesis here as well. Yeah. So in MATLAB, actually, this is a good thing also. If you now close the parenthesis, here, this blinks as well, and it tells you, okay, there is the parenthesis, the corresponding parenthesis opening. Yeah, it's obviously here. Yeah? And this is exactly what we want to have, and we should invert this expression here as well. So we have to invert it as well. Then we take it. We have to multiply it with this guy here again, but without taking the transpose. Yeah, we just copy it, paste it here. Yeah, and that's now our corresponding walled test. Yeah, which is asymptotically. This test statistic is asymptotically distributed as chi-square distribution with 25 degrees of freedom, yeah, or in more general terms, with n degrees of freedom. We have 25 restrictions here, 25 parameters that are restricted, and that's why under the null hypothesis, this test statistic is distributed as chi-square with 25 degrees of freedom. And we can check in our table that you have on Moodle what is the corresponding critical value, yeah, and you will find it's obviously 37.65. Yeah, so if you have a significance level of 5% and we have 25 assets, 25 degrees of freedom, 95% probability, the critical value is 37.65. So whenever our test statistic lambda exceeds this critical value, then we would say, okay, these guys here are jointly different from 0. Hence, we reject the null hypothesis, which means that the 3-factor model here is not able to price our 25 test assets correctly because the alphas here are jointly significant. They are jointly different from 0. And given we have a significance level of 5%, which is common practice, obviously. If our test statistic is less than 30, let's say 37.65, then we would say, okay, we cannot reject the null hypothesis that our alphas are jointly 0. Hence, the three-factor Farman-Friend three-factor model is able to price our 25 test assets correctly, because these guys here are jointly not different from 0, at least not statistically. So that's now what we want to test. So let's run the code and let's see what comes out. Copy now everything. In the command window, push the enter button. And it takes now a while because these matrices are huge, obviously. And the test statistic is 46, 46.09, which means on the 5%, given we have a 5% significance level, we have to reject the null hypothesis, which means the Farman-Friend three-factor model is not able to price our 25 test assets correctly because these alphas here are jointly significantly different from 0. We have to reject the null hypothesis. So Farman-Friend three-factor model doesn't work out for our test assets. Just as you know, the 1% significance level for a chi-square distribution with 25 degrees of freedom is 44.3. 44.3. So even if we would have a 1%, if we would have a 1% significance level as a test level, even then we would reject the null hypothesis, okay? Because 46 is above 44, So obviously our test statistic indicates significance on any level, So the difference between our time series regressions and our cross-sectional regressions that we will discuss now next is that our time series regressions are always more powerful. So basically, cross-sectional regressions and time series regressions should give you the same statistical inference. But if you are deviating, then I would always go with the results from the time series framework, because it's much more powerful. So next, what could we do next? We talked about it on the whiteboard in detail. The only thing that we would need to change, if we would now test, okay, let's not test the alpha. We can also test, let's test if our test assets have a significant exposure against let's say the size factor. We want to test these exposures, this 25 exposures across our assets against the size factor. I want to see if they are significantly exposed to the size factor. So the size factor is obviously the 1, 2, 3. It's the third parameter in our regression equation. So the only thing that we would need to change is this guy here. Okay. Now we can just copy everything, and now our test statistic will test the hypothesis that that these exposures, that our beta exposures against the size factor here would be 0. And let's see what comes out. Copy that into the command window. We have to wait again a little bit. So the test statistic is huge. It's 181. So obviously the exposure against the size factor is highly significant. So obviously size matters here. So let's also check the value factor. Let's check if the value factor matters. The exposures against the value factors jointly significant? Let's again paste it, and it's even higher. So the exposure against the size factor is even more significant. Let's test also just for curiosity, the market factor here, which is the second regressor in our model. Again, copy this into the command window, the enter button, wait a little bit. Yeah, and that's even higher. So the test statistic is 1,411. Yeah, so it's highly significant. So obviously the highest significance here has the exposure against the market factor. Yeah, the cross section here, this beta against the market factors. Yeah, they are obviously most significant here. All right, these were our seemingly unrelated regression model. Now let's turn our attention to Farmer-Macbeth regression. So our task is now use the excess returns of the first 25 stocks of the survivor stock matrix and implement a cross-sectional Farmer-Macbeth regressions using again the Farmer and French 3-factor model. First, test whether the market factor, size factor, and value factor exhibit positive risk premiums. So the lambdas should be the average lambdas should be positive. Which factors are priced? So we have to check obviously also the t-statistics then. Second, can the Farmer and French 3-factor model price the cross-section of expected returns? Perform a statistical test to investigate this issue. So now our 9th task is implementing Farmer-Macbeth regressions. And that's cross-sectional approach. First of all, how do we proceed? So first of all, we have to define our number of test assets, and we actually have it already done here. N is 25. So actually we can skip that. We have K is 3 because we have 3 risk factors on our model. Capital K defines here in this code obviously the number of risk factors, and this is obviously the market factor, size, and value factor. So the first step, if you remember from our whiteboard derivations, is again we have our time series regressions, and we discussed that there are different approaches how to set up Farmer-Macbeth regressions. Yeah, on the whiteboard we started with the time series framework. We started with the time series regressions. Yeah, we grabbed our point estimators beta and we stacked them into a matrix, yeah, into a new matrix which we denoted as B, capital B hat. So again, we estimate regression equation by equation, yeah, the corresponding parameters. Yeah, we grab these, only the betas. We skip the alpha. Yeah, we are only interested in the betas. The alpha we need to include, of course, we need to include a regression intercept in each equation when we run the model, when we run the OLS model in the first step, because otherwise these guys here, the residuals are not 0. Yeah, whenever we have an intercept term in the regression equation, we ensure that our error term is by construction 0. Yeah, and only then our betas are expected to be unbiased. Yeah, we have shown that we made the proof, the mathematical proof on the whiteboard. Yeah, but in order for that proof to hold, we needed to ensure that these guys here are on expectation 0. And in order to ensure this, we have to include an intercept term here. But in the end, if we run cross-sectional regressions, we are interested in the betas, in the loadings against the risk factors only. So we grab these guys, put them into a matrix for each equation. Yeah, we have K risk factors. We have 3 risk factors. So here we have 1, 2, 3 betas for the first equation, for the second equation as well, and for the last equation as well. Yeah, for the nth, the 25th equation, we have also 3 beta parameters that we stack in here, in this row. Then we include a vector of 1s here as well. Yeah. So that's now what we have to do. Yeah, the first step is we create this beta hat matrix. Let's call it B-E-T-A, beta, simple. So it's a zero matrix, and we have 25 acids that we are interested in investigating. So this is a n by k matrix, right? Again, why is it n by k? Because we only are interested in these betas here. Yeah. And we have k risk factors, so it's n by k. So the next step is then, okay, we have again a for loop. For, let's say, n is 1 until capital N, and it doesn't matter if you write here n or I, yeah, you just have to be consistent in your notation, yeah. So you have a lot of degrees of freedom here, how you would like to do what. Again, let's define for each equation our dependent variable. Let's define it as small y. It should be equal to the first column of, it should be the nth column, yeah, and take all time series observations of our submatrix y11. We remember in y11 we store the time series vectors of the excess returns of our 25 assets. So when small n is 1, then this guy here is 1, and it would get you the first column, so the corresponding time series excess returns for the first asset. This is what happens in the first iteration. In the second iteration, obviously, then it would grab you the corresponding excess returns for the second asset. So now we want to define the corresponding vector of ones for we put in the regression equation. It's the intercept term. So it's always a vector of ones, which has a dimension t by 1. And we define it here as simply as constant. Our x1 matrix is defined as obviously our vector of ones, yeah, and our regressor matrix, our factor matrix, right? And we have actually already defined it earlier, so this is the same thing, right? We can also write this guy here directly here in. Or we can define it before. It doesn't matter. It's just different approach. Yeah. So we have now defined our regressor matrix for each equation because it's always the same regressor matrix that we use, of course. So next, our beta hat is, as usual, the same formula that we use all the time. X1 prime itself inverted. And it doesn't matter if you here have parentheses. Earlier I had parentheses. Now I just skip them. It doesn't matter. You can choose times x1 prime times y. And obviously in each iteration, this y changes. Okay, so we get always the corresponding parameter vector here for each corresponding equation. Yeah, in the first run we get this parameter vector. In the second, the parameter vector for the second equation, and so on. So what do? We want to stack this parameter vector, but only the corresponding betas. Yeah, we want to stack them here. We want to store them in our beta matrix. So let's say beta, and we store them obviously in each row. Yeah, the first row is the corresponding parameters, beta parameters for the first equation. Yeah, so we store them in rows at this time. So n this is the row index here. Beta n in all rows. If n is 1, we have the first row, and we have, how many columns do we have? K. Yeah, we have 3 columns here. So if n is 1, this guy here has obviously 3 entries. Yeah. So we have to store which 3 entries here in. We want to have the parameters 2, 3, and 4 from beta hat, because we want to skip. We're not interested in this alpha. So we write it then as beta underscore head start at 2 until k plus 1. Yeah, because beta underscore head is a 4x1 vector. Yeah, so its observations, if you want to have observations 2 to 4, yeah, and k is 3, so we can write 2 to k plus 1. So it's very useful to write the code, and we have to transpose this guy, right? Because we want to store it here in the first, because beta head is a column vector, yeah, but we want to have only, we want to have it as a row vector, right? Because we want to store this guy here as in this row. So we have to transpose this guy, yeah, here. That's important. Otherwise, the dimensions don't line up. So, and it's always useful to write the code as general as you can do. So if you have everything here, should be as general, like we did it now, as general as you can do, so that you just need to define the input matrices here before the loop, yeah, and then you can just run the code for any other model as well, yeah. So that's why it's important to keep the code as general as you can. So we end the for loop, yeah. Let's copy what we did so far into the command window. Let's see what comes out. So let's check where's our beta. It should be now obviously a 25 by 3 matrix, right? Yeah, 25 by 3. And this is exactly what comes out. So we have now our beta, our corresponding the exposure against the Marat vector here. This is for the first stock. The exposure against the size factor is here, and the exposure against the value factor is here. For the second stock, the same thing, and so on. For the last stock, obviously, the 25th stock, we have here the corresponding exposures. So in the first column, we have the exposures against the market factor, for all of our stocks. In the second column, we have the exposures against the size factors across our stocks. And the last column, it has the corresponding exposures against the value factors, for all of our stocks. So the next step is now the so-called cross-sectional regression. So we need to define, obviously, we see that this matrix here has also a constant, yeah. So we need to define this matrix now. And how do we define it? First of all, let's give us constant 1. What's the dimension? It should be a vector of 1s, but it should have the dimension n by 1. Because look at the formula here, we have n test assets, so this guy here should have the dimension n by 1. So this is an n by 1 vector. So that's what we now defined, and we put it into a new matrix. Let's call it beta 1. Beta 1 has now this constant 1 here. This vector of 1s should be here on the first column, and then the rest of it should be this guy here that we constructed. It should be the matrix that contains the corresponding beta exposures. So beta. So that's now a new matrix here. Let's see how it looks like. Let's copy that into MATLAB. Voila. This is now here stored, and it has obviously, it's a 25 by 4 matrix, because we just added here a vector of 1s on the front. Yeah, very simple. So next, what we also need for our cross-sectional regression, we need the vector of expected excess returns. Yeah, so for each of our single asset, we have to compound the sample average, which are the expected returns for each single asset, and we have to stack them into a n by 1 vector, y denoted here as capital Y. So that's what we want to do now. How do we proceed? So we again use a for loop because it's so simple. So our capital Y expected. So that's now the vector of expected test returns is zeros, and it's a n by 1 vector. And here we store in the results, so the sample average of each single asset. And it must be an n by 1 vector. So this is what we will do now. For n is running from 1 until capital N, do what? So y expected n should be the mean, the sample average of what? Well, take the whole column n of our submatrix y11. And it doesn't really matter. You can, if you are better with I, you can write the running index as I as well. It doesn't matter. Yeah, or you can use any other as well. You just have to be consistent here. So let's copy this into MATLAB and see what happens. And let's take our y expected. Let's see what it is. Yeah, it should be exactly the correct dimensions, 25 by 1. And this is now what it is. Yeah. So this is the vector of cross-sectional returns. Yeah. So the first entry here is the average return from the first test asset. The second entry obviously is the average returns of the second test asset, and so on. Yeah. So now we have, I guess, the ingredients that we need, and now we can compound our lambda hat, which is the vector of risk premiums. So, and again, this formula is nothing new for us anymore. So we transpose this guy times itself inverted times transpose this matrix here times our vector of expected returns. So let's implement it. Let's call it lambda is equal with what? So take beta 1 matrix, transpose it times itself inverted times itself inverted times y underscore expected. Yeah. So we regress the vector of expected returns of our cross-sectional vector of expected returns on the corresponding beta matrix. Yeah. We regress this on the beta. So this here basically, it tells us, yeah, if the betas explain the variation in cross-sectional returns. Yeah. Does the variation in betas explain the variation in expected returns? Yeah. That's the cross-sectional approach. So let's check what comes out. Let's copy this into MATLAB. So what we see is obviously 0.26, so which is the part of the unexpected returns that are unexplained by the average risk premiums related to the market factor, size factor, and value factor. What we see also here is obviously that the risk premium for the value factor is negative. Yeah? So that's obviously something weird. It should not be like this. The risk premium for the market factor is 0.55% per month. The risk premium for the size factor is 0.35% per month. And now we have to check, okay, now we have estimated the risk premium. So obviously the risk premiums are positive for the size factor and for the market factor. Now the question arises, which factors are priced? So obviously, we need to compound the t statistics in order to be able to make a conclusion here which factor is actually priced, because they could also be statistically not different from 0. They could be statistically 0. So we have to test this. So how do we proceed now? So we have to estimate now, or we have to construct now a matrix where we store for each point in time, we store the corresponding cross-sectional risk premium vector. So how do we do that, and what does that mean? So first of all, let us construct a matrix. Let's call it lambda, and it has zeros k plus 1 by t. So we have our risk premium vector lambda. It has four different estimates. We have the intercept term, this lambda 0. We have the lambda 1, lambda 2, and lambda 3. Lambda 0 is, again, this is the part of the expected returns that is unexplained from the variation in the betas against the market factor, size factor, or value factor. If we take the mean of y expected, it's 0.62. So the cross-sectional average of average returns is 0.62. So across this time span that we consider here, on average, these assets have generated 0.62% per month. And from this 0.62%, 0.26% remain unexplained of the exposures of the variation in betas. Okay, this is basically what this means. This lambda 0. Okay. So, but now one more time. So we have 4 case 3 plus 1 is 4. So we have 4 risk premiums, and we have t times these observations. So now we want to store for each point in time, the corresponding risk premium vector, lambda, for each point in time. So we have to estimate now capital T times the lambda, which has the dimension 4 by 1, and we stack it. Always we store it in each column of our lambda matrix. This is what we want to do. So let's run a for loop for t in order to denote the time index. But as I told you, we can use here anything. T is 1 until capital T. So what should it be? What do we want to store in the column T? So if T is 1, we store something in the first column of our lambda matrix. In the next iteration, when T is 2, we store something in the second column. So what do we want to store? So let's take our beta 1. We do the same thing. So we keep keep this constant here, this part, and now we let this guy here vary. This guy here now changes. For each point in time, we take the cross-sectional return vector. So this guy here, what is here, should be n by 1. So again, so we take our matrix from here. We just copy what is written there. And now say, okay, in the first iteration, we take we take the entries, all entries from the first row, yeah, and we have to transpose it. So what is in the first row of our Y11 matrix? Yeah, when t is 1, yeah, we regress the first row of Y11 on our beta matrix. Yeah. So what is in the first row? In the first row of Y11, we have the corresponding access returns for our n stocks, right? For point when t is 1. Yeah. So that's a 1 by n vector. The first row is a 1 by n vector. We have to transpose it so that this becomes a n by 1 vector. Yeah. So that we can do this operation here. So that's why we have to transpose this guy. Yeah. We have to transpose it. So we do this. Yeah. We go through this vector here. Yeah. For each point in time, we always take the corresponding row, the whole row, which has the vector of cross-sectional returns, exact returns for each point in time. Yeah, we do this for capital T times. Yeah, do it 497 times in each iteration. Yeah, so what we get is then the corresponding risk premium vector for each point in time. Yeah, of a cross-section, because this is a cross-sectional vector here. So okay, we have done this. We can now end our loop. Yeah, and our lambda here. This is now the matrix where we store everything in. So let's copy this into our workspace, into our command window. Now it says that some dimensions are not correct. What can it be? Okay, this is lambda, and this is lambda. So I had here obviously an error. I cannot even write. Funny. Okay, let's copy this. Let's check how our lambda looks like. So our lambda should have the dimension, so 4 by t, yeah, and in each column should be the corresponding risk premium vector for each point in time. So let's go back to lambda. Where do we find our matrix here? Here, yeah. So we see it's a 4 by 497 vector, but it has obviously, okay, this is the wrong lambda. We can delete it. It's lambda with a b in between. So here we have it. So we have here for each point in time. So we have 497 time series observations. So we have here in the first column, these are the corresponding risk premiums, lambda 0, lambda 1, lambda 2, lambda 3, yeah, for the first point in time. Yeah. This is the cross-sectional risk premium vector for the first point in time. This is the cross-sectional risk premium vector for the second point in time, and so on, and so on. So if we want to have so obviously in the first row, yeah, this gives us the lambda 0, so the unexplained return part across time. Yeah, we can also plot it. Let's just plot it. Plot lambda, and we want to plot the first row. Yeah, because in the first row we have the lambda 0. So let's do this. So this is how it looks like. So there's obviously a huge amount of variation across time. Yeah, it's very volatile. So in here, obviously, we have the financial crisis where everything went weird. So there's a huge deviation here, obviously. Yeah, because returns are so noisy, it's maybe not so surprising. So what's the mean? Let's take the mean of the first row. What is that? It's 0.2653. And this is exactly the same value that we have here. Yeah. So it gives you basically the estimated, the average risk premium. Yeah? The average risk premium is the same thing as if you take here from our lambda matrix, the average of the first row. It must be like that by construction, right? It must be like that. So this lambda matrix gives you just the corresponding variation across time of that respective lambda estimate. So if you want to see the risk premium that is related to the market factor across time, yeah. So we can plot lambda 2. So we plot now the second row here from our lambda matrix, yeah, and it gives you the evolution of the risk premium associated with the market factor, yeah, modeled via the market sensitivities, via the betas across time, and this is what comes out. Yeah. You see also here obviously a huge variation. The risk premium is very volatile. So if it would be significant, obviously we should have much less variation here going on. So the same thing is obviously if we take the risk premium for the size factor, it's also very volatile. They look very different. They look very similar. And for the value factor as well, you see. We also can plot the risk premiums for the value and size factor together. Then again, what we have to do is, okay, we have to add this kind of brackets, yeah. And let's copy this. This should be now 3. This is 4. We have to close these brackets here as well. We can just push the button here, and it should give you actually. Are they overlapping so much? Obviously. Well, then it is what it is. So that's basically what comes out. And now the corresponding t statistic. So what do we have to do? Okay, we go to the estimated risk premium vector, the average vector, lambda. Let's take the first element, which is the corresponding estimate for the average unexplained part, yeah, which is the lambda 0. When we divide it by the square root of the variance from lambda, take the first row, all columns, divided by the observations t. Let's copy that. So MATLAB gives me a note that here that I have a typo here. So once again, yeah. So the t statistic obviously is 0.72 for lambda 0. Yeah, that's for lambda 0. So what does that mean? So it means obviously that the part that is unexplained, yeah, this 0.26, is statistically not different from 0, because we have to compare this value here with the normal distribution, right? The t statistic, if you remember, right? The t statistic, yeah, we have to compare with the normal distribution, yeah, which has obviously, and the corresponding critical value is 1.96 or minus 1.96, given we have a 5% significance level. So obviously 0.72 is less than our critical value of 1.96, which implies, given we have a 5% significance level, we cannot reject the null hypothesis that our lambda 0 is statistically not different from 0, yeah, which means in turn, it means actually that our Farman-French three-factor model is obviously able to price the cross-section of expected returns correctly. Otherwise, if this 0.26 would be significant, this guy here should be much larger than 1.96, right? So there's no average mispricing going on. But this result, obviously, is in opposition to what we have retrieved from the time series framework. Yeah? From the time series framework, we have seen that the alphas are jointly significantly different from 0. So what should we trust now? Yeah, what should we trust? So obviously, in this case, you should go with what the time series regressions are telling you. Yeah, because this obviously, it's very unlikely that this result is trustworthy. Yeah? And we will also see now what comes out for the other guys here. If we now estimate if the risk premium associated with the market factor is significant, the only thing that changes here then is we have to take the second guy, yeah, in our lambda vector, and we have to divide it by the square root of the variance of the variation here, yeah, of the second row in our lambda matrix. Yeah, so that's how the t-statistic is defined. Copy that into our work, into our command window, push the button. So obviously, not even the variation of the beta against the market factor is priced, because obviously the risk premium, of 0.55, which is the average risk premium related to the market factor, is obviously statistically not different from 0. Yeah, because the t-statistic is below 1.96, which again doesn't make much of a sense, because we found in the time series framework, when we were testing the betas against the market factor jointly, we have seen that the test statistic had a value of 1,400 something. Yeah, it was highly significant. So the market beta matters. But here in the cross-sectional framework, it seems to be insignificant. And the same is if we now take the lambda against the size factor. See what comes out here. Yeah, also here, this 0.33% per month is obviously not different from 0. So the risk premium related to the size factor is obviously statistically not different from 0. Yeah, which also doesn't make much of a sense. So if we see, so obviously in this model here, none of the risk factors has significant risk premiums. Also the value factor, you will see, has a risk premium that is not significant. It's almost significantly negative, actually, on a 10% level at least. Yeah, you see the test statistic, if it's less than 1.96, it would be statistically significantly negative. Yeah, but if it's a risk premium, it should be positive. Yeah, so the value factor should carry a positive risk premium, which should be reflected also in the cross-sectional framework, but it doesn't. So that's a problematic thing. It could be sample specific. It could be due to the high volatility. There are many different explanations. Another issue could be the framework that we here derived, our cross-sectional, our Farman-Macbeth approach that we made use of here. It obviously doesn't account for the variation in the betas. Yeah, you see, the betas are assumed to be constant across assets. This is a strong assumption, and people in finance say that obviously that in the long term beta is constant, but we have seen earlier that the beta can vary over time. Yeah, some growth stocks become value stocks for certain periods in time, and then they turn into growth stocks again, or some stocks have co-move with the market factor a lot, and then after some time they are almost uncorrelated with the market factor. So in order to address this issue, some people implement they basically estimate step by step. They estimate time varying betas. Yeah, so let's say you take the first 60 observations of the sample. Okay, you estimate then equation by equation the corresponding beta estimates for the first 60 observations. You get your vector of risk premiums using the first 60 observations of the sample. Yeah, then you move this time window 1 month forward. Yeah, again, you get new estimates for the betas. Yeah, and you get and using this cross-sectional regression framework, you get also a new estimated risk premium vector. Yeah, and you store it basically then in a matrix. So you basically you replace this lambda matrix here that we now estimated using a constant beta matrix, using always updated beta matrices here, right? This is what happens then. So there are obviously different ways to address this issue, and other people, they use bootstrapping procedures. So they basically they resample the matrix of risk factors and also the matrix of excess returns. This is also something that you can do because it somehow obviously gives you also varying betas. And using bootstrapping procedures or resampling, you could also get, you would get basically always new estimated lambda vectors, for each artificial sample or for each synthetic sample. This is something that we will do in the follow-up course here that I will teach next year in spring. There you will learn some very sophisticated bootstrapping methodologies that basically allow you to account for any kind of dependency structure in the data. So you will learn to create synthetic data and re-estimate parameters, store them in a matrix, and you will be able to calculate the true sample covariance matrix, via resampling. Yeah, but this is what we do not do in this course here, because in this course here you just should learn the simple basics, and you should be able to translate econometric formulas, simple econometric formulas, into MATLAB, and put them into some for loops, because obviously you can do many things here. But important for me is that you know what you are doing, and that's why you need to know what's behind the matrices that we here defined. So that's obviously very important, because you have seen that you can very easily confuse things. You can, if you don't get the dimension straight, if you miss here the transposed sign, obviously the code doesn't work out, and so you have to know what you are doing, and that's why it is important that you understand the matrix operations and the econometrics behind all what we do.